Okay, it's recording, so let's get started to the last lecture of the Dark Matter School program. And just to let all of you know that if you're watching this lecture for the first time, I advise you to go back 9 lectures, and where we started from the very beginning, going to cosmology and introduction to particle physics, and then we delved into the dark matter world. Okay, so let's continue with dark matter complementarity. I'm gonna share my screen. Just a second. Yes. All right. So we are going to start lecture 10. Someone said something? Okay. So we're going to start lecture 10. So in the lecture 10, we are going to cover dark matter complementarity, which stands for searching for dark matter using different and orthogonal data sets. So when we discuss dark matter complementarity in the context of usually collider physics, direct detection, and indirect detection, these 3 things. So that's when these names are faced. Are searching for dark matter at colliders, searching for dark matter at underground laboratories, and searching for dark matter in the sky using gamma rays or cosmic rays or whatever, X-rays, etc. So I'm going to continue with the scenario that I proposed in one of the lectures before, which was the scenario where we had a dark matter that finds another anti-dark matter particle, and then they find each other, and let's say they produce some pairs of Fermi and anti-Fermi. And I believed, and I focus on a Z boson. So let's suppose that Z boson is the mediator between the dark sector here and the visible sector. So visible sector, and it's called dark sector. So visible here has nothing to do with charge, electric charge. It just means the standard model spectrum, and dark sector is just whatever it is within the dark symmetry. So when, for instance, if we have a mediator which belongs not to the standard model spectrum, but to something else, for instance, the Z boson here belongs to the visible sector. However, if I had put there a Z prime boson, that guy is called the dark boson. Okay, so it just refers to the case where if it belongs to the standard model spectrum, it's called visible. If it's not, if it doesn't, then we say it's dark. So we have the dark sector and the visible sector. So now let's try to see how things they play out when we are discussing dark matter complementarity. So let's the first thing I'm going to cover is the abundance. So the abundance of dark matter. So the abundance of dark matter in this case will have a feature like this. So omega h squared, when you plot it as a function of the dark matter mass, you're going to see something like this. So it starts with a very large abundance, and then it starts decreasing with the mass, and then eventually that dark matter mass reaches the resonance, the Z resonance, and then it will drop like this, and you'll rise up again, and I'm going to explain why it's going to rise up, and then it starts decreasing again. So this will be the abundance. And let's say the correct value for the abundance, which is 0.1 according to Planck, 0.1, 0.11, 0.12, and then is a horizontal line like this. So it means is that in 3 points, the correct dark matter abundance is satisfied around here, there, and there. So one where the dark matter mass is very, very large, and another where you are near the resonance. So this peak here happens when the dark matter mass is the Z mass over 2. Remember, so when the Z boson, when the center of mass energy, which is 2 dark matter mass, twice the dark matter mass, matches the mass of the mediator, you have a resonance. Therefore, usually what you find in S-channel models, not necessarily a Z boson, could be a Z prime or a scalar or whatever, whenever you have a resonance or S-channel diagram, Feynman diagram, there are 2 M's here. When you have an S-channel diagram, what you're going to see something like this. The abundance starts at very high and then drops when you reach the resonance, and then rises up again and then goes down again. So let's try to understand now how you can understand this shape. So first, I'd like to ask if anyone in the audience there in the meeting knows how to explain this behavior for the dark matter abundance. Anna, Julia, and Luca. Does any of you know how to explain why you see this behavior? No one? Okay, so I'll try to address it. So the reason goes as the following. So I have dark matter here, chi, emits another chi, and then annihilates and produces fermions. So the heavier the dark matter particle is, the more annihilation channels I can have. They are accessible to the dark matter particle. So as I increase the mass, I increase sigma v. As I increase sigma v, the abundance decreases, because in the freeze-out scenario, the dark matter abundance is inversely proportional to the dark matter annihilation cross-section, or the thermal actually, right? But let's call it the annihilation cross-section. So as I increase the mass, the abundance decreases. So as I decrease the mass, at some point the abundance is very, very large, because I don't have many channels accessible to me. So I cannot annihilate much. I can annihilate only 2 electrons. And as I increase the mass, now muons, and increase the mass, now taus, increase the mass at B quarks and C quarks and so on. So the more, as I increase the mass, the abundance decreases, because more of the dark matter pairs are annihilated into something. So they stop existing to produce something else. So that's why you expect to see this behavior. Let me see if I get around here. So this has to do with just the fact that omega h squared is proportional to 1 over sigma v. The same thing happens here. So it has to do also with the omega h being proportional 1 over sigma v. And the one in the middle, this one, has to do with the resonance. So, and the shape of the peak has everything to do with the shape of the decay width of the Z boson. So the larger the width of the Z boson, the larger the fatter will be the resonance. So let's say that this Z boson is very light. If the Z boson were very light, so I'm gonna draw now a case where I have omega h as a function of dark matter mass, m chi, and now I'm gonna draw one where the Z boson is light, very light, and the resonance, the peak will go like this, sharply, and then decreases. Let me do it more, not as drastic. Okay, so that's a light Z boson. Obviously, the Z boson mass is fixed because it belongs to the stellar model, but I'm talking in general, whether it's a Z boson or Z prime or a scalar or whatever. Okay? However, if the Z boson was very heavy, very heavy, the thing will happen to this. Someone asked the question? Okay, no. If the Z boson was very large, there are two things that happen in this plot. So let's think of this. So again, why it's not, okay. So I have this annihilation channel. If the Z boson is very large, very heavy, the annihilation cross-section drops, right? Because the larger the heavier the mediator, the smaller the cross-section. The smaller the cross-section, the larger the abundance, right? So it goes the opposite. So when I go to a heavy mediator, this thing will start from very high above. Since it's a heavy mediator, the resonance will not be so sharp, it will be broader. It will be like this, like a fat resonance. That's how we say it. And we'll drop like this. And then goes again. And it doesn't have to be as high. But the only thing that will happen for sure is that you'll be fatter. And this width has to do with the width of the Z boson, or whatever the mediator is mediating the interactions between the standard model and the dark sector. Okay? So everything is embedded in the width of the Z boson, or the mediator. And the width is proportional to the coupling squared times the mass of that boson. And why is that? Well, obviously, you have a Z boson that goes and decay into pairs, fermion pairs. And this coupling is proportional to G. At the amplitude level, I have to square the amplitude. And then I get a G squared dependence. And I also have a MZ dependence, because the heavier the Z boson, the more channels I can decay into. Therefore, the larger the mother particle mass, the more channels I can produce, I can decay into. Therefore, the decay rate is proportional to the coupling square times the mass of the mediator. Okay? So it's just, I mean, physics. I'm not even computing anything here. I'm just explaining to you how this thing works. And then if you compute it properly, that's what you're going to find. You're going to get some extra factors, which is related to the mass of the fermion, the final state, the mass of the Z boson, whether it's a pure vector coupling or axial coupling, blah, 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 blah. But that's what you get. Okay, that's proportional to this. Okay, and so now you understand why sometimes you see this behavior when you're talking about dark matter production and the early universe, and how it's related to the dark matter mass and the mass of the particle that mediates the production. Any questions so far? No? Okay, one, abundance of dark matter. Let me just erase here. So let's discuss now the scattering of dark matter. So I had this diagram. Now I'm going to just remove this bar for convenience, and you're going to see soon why I removed it. So I'm going to flip this diagram, rotate in this direction. Then I have chi, Z, fermion. So now that was annihilation. And now this is scattering. The difference is, well, you had dark matter in the initial state, and you no longer have dark matter in the final state, so you annihilated. In the scattering, you do have a dark matter particle in the initial state, and you're still going to continue to have a dark matter particle in the final state. Okay? And the scattering, the cross-section you find for both cases are different, Well, one experience of resonance. This one is scattering, does not have a resonance. Okay, well, in most cases, right? Because the momentum transfer here is proportional to the momentum transfer will be dictated by the mass. This guy is at rest usually, so the momentum transfer to this case, what you have is the momentum transfer, the momentum of the Z boson will be governed by the energy of chi, right? In this case, the energy of the Z boson is twice the dark matter mass. Okay? And in this case, you have a reduced mass, which is chi and fermion, which makes the momentum transfer to be really, really small compared to 2m chi. So the center of mass energy here is 2m chi, and here is proportional to reduced mass, right? The momentum will be the reduced mass of this times v squared. In the reduced mass, the mass of the fermion is negligible. P is reduced mass times, let's say, velocity. And the reduced mass m of the fermion, let's say, times the mass of the dark matter over mass of the fermion plus mass of dark matter. However, this is not a fermion. What happens in practice is not a dark matter scattering a fermion, it's scattering a nucleus. So you have Mn and have Mn. So the mass of the nucleus, usually we are talking about of, let's say, 100 of GeV. So if you put it this as 100, you see that this momentum will be very small, and V is 10 to minus 3c, which is the average velocity of dark matter particles in our halo. So this is a very small number compared to this case, okay? So the center of mass energies of these two processes are completely different. Okay, that said, so how am I going to compute this? So I have a scattering, computing. The scattering cross-section, sigma as E, for a spin dependent. So I'm assuming the scattering does not depend on the spin of the target. Okay, spin independent will be given by the reduced mass squared times the gauge coupling that appears here. Let's say G and G. Well, I'm assuming that dark matter cup interacts with the stellar model forms through a Z boson, and that interaction is proportional to G, the SU2 gauge coupling, G. So you get a G factor here, G factor here is G squared. But then when you square the amplitude, you get a G to the 4th power. The same for the mediator mass. You get an M squared when you square it, and then you have an MZ to the 4th power. And believe me or not, but the only difference between the things I just argued here, the difference between this result you see here and the actual result, if I do the whole calculation, is a pi here. If I had completed everything, like computed the amplitude and so on, blah, 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 taking into account some of these spins, blah, 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 everything that's taking the resonance, take the propagator, the only thing difference is a pi here that appears. That's the correct result. Truly, the correct result is this one. Times some constant factor here, which has to do with the things that I didn't discuss, which is the charge of the dark matter particle under the gauge symmetry, in which it makes the dark matter particle stable. But I didn't discuss this. That's why I don't want to bring this into the game now. So this is scattering cross section. So let's look at this behavior. So as you see, this is equal to mu is mn squared m chi squared over pi mn plus m chi squared times g to the 4th mz to the 4th. So it means this: if I fix g and the z prime and the z mass to be a constant, and mn is the mass of my target, is also fixed. Therefore, the scattering cross-section grows with the dark matter mass, well, what you get is SE will be controlled by Mn squared, M chi squared, sum of Mn plus M chi squared, right? So if then we consider the scenarios. In scenario at which M chi is much lighter than the Mn, so I get Mn here, and then get Mn there, where squared, they cancel out, right? I guess I just M chi squared, right? Behavior. So it's sigma SE is proportional to M chi squared, right? If M chi is much greater than Mn, and then sigma SE will be proportional to M chi much greater than Mn, then I just give M chi squared. The M chi squared cancels out with M chi squared. I got just proportional to Mn squared, which is a constant, right? So therefore, what you expect, a plot of sigma SE as a function of the dark matter mass is something like this. Eventually grows with M chi, and later becomes a constant. So that's the kind of plot you're going to see for every single S-channel model, where you have a spin-dependent scattering, does not depend on the nucleus spin, and you have a very light dark matter particle mass, have a light dark matter particle, and then as increase the mass of that dark matter particle, and the scattering cross-section becomes a constant. So this is important for the fact that this is a theory, right? This is just my model. It's my model. It has nothing to do with the experimental limit. Okay? Make sense? This is just, I'm just plotting this function. That's all.
I think in that paper that you and Klassen wrote, there is this curve.
Yeah. Yeah, it's not just the paper I wrote for Klassen. In all papers with S channels, they have this.
The first time that I saw this kind of
behavior. So that's what you see. And to be honest, to be really honest, first time I wrote a paper on dark matter, which had the spin dependent in the mass, I did not understand myself why this was the shape. Nobody taught me, so I just say, okay, I accept it. I ran micro megas, and that's what he gave me, so it gave me, so I think it's correct, because everybody uses micro megas, so I believe it's correct. So, and this, I wrote a paper, but I did not fully understand the result that micro megas was providing to me, because I did not understand the physics. I understood how to code, but not the physics behind it. Okay, so that's what you see, and that's the theory, right? However, the experimental limits, they have this shape, and now you understand why. Right? Fine. So it means is, if I have a very light dark matter particle, maybe my theory obeys the limit from direct detection. But as I increase the mass, you would think for collider physics, as I increase the mass of the particles, they become unreachable by colliders because the mass is too heavy. You cannot probe it. For dark matter physics, that's not the same, because as you increase the dark matter mass, you don't decrease the scattering. You're actually making it to be constant, right? And the limits, the experimental limits, sure, they weaken with the dark matter mass, right? This has to do, if we explain to this, has to do with the number density being rho over m. As you increase the mass, the number density decreases, then that's why the limits from the direct detection rises up and become weaker. They weaken with the dark matter mass. But they cannot be too weak. Perhaps sometimes they're not too weak to salvage your model. So your model can still be excluded. So when people say, I have a model of 1 TeV dark matter particle which is excluded, let's just make it 5 TeV and it's fine. No, it has nothing to do with 5. Because if you increase from 1 to 5, your theory is the same as far as direct detection is concerned. And the limit weakens by 1 over 1/5. Right? Because you had 1, and let's say, for instance, like this, rho is 1 over 1 TeV. And now I make it 5 TeV, so it's 5 TeV now. So the limit will decrease, will weaken by 1 over 5, roughly. Okay? Assuming all techniques are the same, the experimental way, the way how you detect the 5 TeV is the same, everything is the same. The way there is no, remember the inelastic scenario when the momentum is too large and you have a drop. So let's set this aside for a moment. Let's just think of this experimental limit. So naively, you would expect the experimental limit will decrease by 1 over 5, will weaken. But then your limit, your theory is still the same as far as direct detection is concerned. But the limit decreases. But now you're going to see the difference. And let's say I increase even more the dark matter mass. I'm here. And then sure, eventually the experimental limits will be too weak, and now your model survives the exclusion limit, because exclusion limit is saying that everything above the blue curve is excluded. See? So sometimes resorting your model to a heavy dark matter particle scenario is a way to bypass the limits from direct detection experiments. Okay? That's typically true, but the mass you have to increase really, really so much, you know. It's not just a little. From 1 to 2, you're gonna now be free from direct detection. No, you have to increase a lot, because the direct detection limits, they decrease, they weaken with 1 over dark matter mass, roughly. Make sense? Any questions so far? Okay. So that's one way. So now you're going to see why direct detection limits are the toughest ones to obey. Because you've seen so far that the relic density, let's say, as you see from this plot, for instance, in this scenario here, let me draw again let's say the correct abundance from Planck was around here, 0.1. And then in my model, the red light Z boson scenario, I have a dark matter abundance the correct dark matter abundance here, here, and there. Then I change the mass of the Z boson. I won't change the mass of the dark matter particle. I just change the mass of Z boson. Or I just change the coupling. And then let's say I just change the Z boson mass, as that was the scenario we conceived. So I had a Z boson there, which was heavy, and then the width of the resonance becomes larger, broader, and then the points at which I get the right relic density are there, there, and there. So it means is I can shift the regions at which I can get the right relic density just changing one coupling. If I change just one thing, the Z boson mass, that's all. I change the whole region of Fermi space at which the correct relic density is satisfied. Okay, just change one. I could change the dark matter mass won't change much, but the couplings will change a lot. Okay, because the sigma V, not the thermal, the sigma V for an interaction which is chi bar z fermion, this sigma V will be proportional to this coupling to the 4th power over the mass of the Z boson to the 4th power. Okay? And there will be some dependence on the dark matter mass, but it's not so large. Okay? There will be some dependence, some log dependence on dark matter mass. But you see, a tiny change in Z to the 4th power, or a tiny change in the Z mass will change the sigma V to the 4th power, or the abundance by the 4th power. So drastically change the overall abundance when I change the mass of the mediator or the gauge coupling or the coupling involved. And the same for direct detection, conversely to direct detection, because direct detection, you change dark matter mass, you're not going to change much your theory. Your theory continues to be the same, right, for heavy dark matter. For light dark matter, yes, it does change, but eventually won't change much. The only thing I can change for real, again, is here. See? G to the fourth mz to the fourth. So if I change the coupling or the mass of the mediator, the scattering cross section will drastically change, because it's similar to direct attack to annihilation or to the abundance. When I change the coupling or the mass of the mediators, oh no, I don't want this. When I change this thing, then I really change the scattering cross section. And in my assumption here, remember that I fixed this ratio, right? So the only way I can really change the abundance and the scattering cross section is by changing the ratio between G and mz to the fourth. Make sense? So you see, what's the problem there? The problem is that you have the same ratio in both cases. You have G to the fourth. Oh, come on, wait, it's freezing. Hold on a second. Okay. Hold on, it's too slowly. Come on, come on. Okay, so here. So you have a, sorry. What's going on? Yeah, it's just too slow, it's freezing. So let me save this file before I lose it. Come on. Yeah, hold on a second. So are there any questions for now? So what I was trying to emphasize that the ratio that dictates the sigma v is the same ratio that governs the scattering cross section. That's why it's tricky, because you want at one hand obey direct detection bounds, and on the other hand you want to get the right relative density, but they are both controlled by the same ratio. So if direct detection says, look, this ratio is ruled out, what are you going to do about the relative density? Because the way it goes is the other way around. First, you want to at least satisfy the relative density, because otherwise you don't have a concrete dark matter model. Your model has to explain the correct relative density, has to give you that. Yeah, I think maybe it will be better now. Yeah. So you want to get the right relative density, so you have to fix your G over mz to the fourth ratio. Okay. And the same happens for direct detection. So it's tricky. And in many cases, what happens is the following. So let me write down now here. Let's say combining direct detection plus relative density. So what happens is you have a plot. Let's say this is the mz mass and this is the coupling. And what happened is the following. So now I'm going to drive the same resonance curve, but in a different plane. So I fixed m chi to be some value. It's fixed. And then you have a plot which goes like this. And this plot is where omega h squared is equal to 0.1. Along the line, as long as you are on top of the red line, you satisfy the correct relative density. Okay? Fine. And this, remember that omega h squared is proportional to 1 over sigma v. And this is mz to the fourth over g to the fourth. Because sigma v is g to the fourth over z to the fourth. Okay? I just took the invert of that. The inverse of that. Okay, fine. And then now I have direct detection. Sigma SE is proportional to m chi squared mn squared over m chi plus mn squared. And then I have a coupling squared fourth and mz to the fourth. And then what happens is, as the limit, as you see, if I plot in a log-log scale, this is just gives me a number. In a log-log scale, this will be 4 times the ratio, right? The ratio in a log of SE, sigma SE, would be 4 proportional to 4 G over MZ, right? So it means is in a log-log scale, what I get is a line like this. As I increase, now let's understand it. So as I increase the mass, the Z mass, okay? As I increase the Z mass, my SE decreases, right? Okay? So along this ratio, where MZ, ratio is 1, okay? It's a constant. I'm not changing sigma SE, okay? Agree? Okay, fine. As I move to the left of that dashed line, what I'm doing is I'm going to values at which MZ grows faster than G. As MZ grows faster than G, then that means that sigma V is decreasing, okay? Because this ratio is G over MZ. So as I increase MZ, go to the left, increasing MZ faster than G, then my sigma V is decreasing. My sigma SE is decreasing. If my sigma SE decreases, the weaker are the constraints from direct detection. Okay? So let's say this direct detection is there. And as I move, for instance, what I'm saying is the weaker, right? So it means that everything here is okay and everything for here is excluded. Because as I go to the right, I'm increasing G faster than I increase MZ. Therefore, the direct detection limit. So if this thing grows faster, then the sigma SE grows faster, and then the stronger is the constraint from direct detection, the more excluded I become. Okay? So, and then that's for dark matter mass. I said dark matter mass is fixed. And then you say, let's say that my scenario here is that, remember, Z is just a representative particle, right? And this peak here happens precisely when the MZ is twice the dark matter mass, right? That's where that peak happens. Because it's the resonance. The resonance is when the mediator is twice the dark matter mass. Remember, the diagram I had was this one, right? And remember, this curve in red is for the relative density, not for the scattering cross-section. But I can now place everything, put everything together in the same plane because they are related to the same diagram. I just rotated. I had this diagram here. And this one here is the same. Apart from some small differences, it's the same. Basically the same. I just rotated. Okay? This coupling here is the same as this one. This coupling here is the same as this one. This particle here is the same as this one. See? There'll be some differences, sure, because this chi bar, one when you compute Feynman diagrams, amplitudes, one comes, anti-particle comes with a different spinner compared to a particle. Sure, you're going to compute that, but okay, it's not much big of a deal. Okay, it's not something like intrinsic, super different. So some of the spins will be given by, it will result in a different number. One is plus p slash minus m, the other one's p slash plus m. Okay, so what? The minus m or plus m, not like m squared or m to the fourth. It became something p to the fifth power, something really changes, you know, just changing the traces at the end. Okay, so you see, now you look at this diagram, and that's, now you're gonna understand why direct detection experiments became so important. Because they are, in many models, they are connected to the relative density. The same way as many of you know indirect detection is. Indirect detection is probing sigma v, right? Which is the same sigma v that enters in the abundance, the same, because the abundance is the thermal. In this, what you are probing is not the thermal, it's just a sigma v using direct detection, but it's sigma v, okay? But in many models happens that the same couplings, the same parameters that control the relative density are the parameters that control the direct detection. And the direct detection experiments have experienced a significant improvement in their limits. So they change their limits 1 order of magnitude a year. That's insane. So they improved many orders of magnitude in a year. So soon, this limit, which was in blue, at some point was here. So let's say in this limit, okay, let me change the color. So this uniform direct detection at some point was around there. So that was the limit, direct detection old. And eventually they started excluding the whole parameter space, because everything to the right of the blue curve is excluded. Everything to the right of this, you know, pink, whatever, is which color is this? Purple. Yeah, magenta. Magenta color, everything to the right is excluded, but as direct detection experiments witness a significant improvement in their limits, we have witnessed this. And then they start excluding a large portion of parameter space. And that's why you're going to often hear in conferences, people say, look, we have to live at the resonance to survive. Why? Because I need to, my parameter space, the only thing that's left is this one, this peak right here, which is on the top of the resonance, because direct detection have just killed them all. Okay? And say, okay, Fernando, this is true for all models? No way. Okay? Sure, there are many models that do not experience this very restrictive limits from direct detection experiments. But those ones that which are often have gauge interactions, like a Z boson would have, a Z prime would have, these scalars are still quite excluded in many cases. As long as you have a resonance, most of the scenarios which you have a resonance are excluded for dark matter masses below 1 TeV. But say, oh, for now, if I go much heavier than 1 TeV, well, if you go from 1 to 2, it won't change anything, because the scattering cross-section does not change much. But if you go to very, very heavy, 10 TeV, 12 TeV, yeah, sure, then the direct detection limits weaken with one over dark matter mass, and then eventually you're going to be okay. Okay, but you have to be a 10 TeV, 8 TeV, something like this. You have to increase a lot the mass. Okay? Any further questions?
Professor, just for a complement, you cannot make the mass too large because you have theoretical constraints from unitarity, for instance. So
from? No, those limits from unitarity, yeah. So if you are in the freeze-out scenario, the unitary limits are valid. If you depart from freeze-out, those limits from unitary are no longer valid. No longer valid.
Just for freeze-out,
so you can bypass these limits from unitarity. It's not very hard.
Interesting.
Okay. Okay, fine. So let's now discuss some ways to avoid these limits from direct detection. So as you see, in this scenario I discussed, the annihilation rate and the scattering cross-section are closely related up to some constants. Therefore, the easiest way to avoid direct detection limits is to disentangle annihilation cross-section and scattering cross-section. And to disentangle annihilation cross-section from scattering cross-section is to somehow have a new production mechanism for dark matter, which is different from just annihilating into stellar model fermions. And to do so, for instance, there are scenarios at which you have a new production mechanism of dark matter. So for instance, one of them, which has become quite popular, is that, okay, I have dark matter here, and they annihilate and produce fermions, and that's the yield, right, which is number density over the entropy, and the plot, it goes like this, right, in equilibrium. However, there is a freeze out, and because of freeze out, this thing goes like this. That leads to omega, let's say h squared equal 0.1. So it means this, let's say the annihilation cross-section I need to get this relative density right is the one that is the thermal one, the canonical thermal one, which they call 3 × 10⁻26 centimeter cube per second. Remember, the thermal, not the sigma v, but let's assume them to be the same. Okay, I'm going to start in the scenario which is the most restrictive scenario, at which the sigma v is equal the same thermal sigma v, the relative density is just 0.1, the sigma v is 3 × 10⁻26, then I can probe it and so on. And the masses are below 1 TeV and so on. Everything I can exclude. In the range I can probe it and exclude it potentially. So now it's 0.1. So I can exclude this cross section, right? And now I'm going to consider the scenario at which the sigma v is too small. Okay, if it's too small, let's say around here, the freeze out will happen earlier in time. Because remember, the larger the sigma v, the more I retain equilibrium. So it's smaller, so it's around there. So sigma v here is around 10⁻27 centimeter cube per second. So sigma v is too small. If sigma v is too small, means the abundance of that dark matter particle there is too large. So if we say we overclose the universe, overclose. Okay, that's the expression we use. Why? Because omega total should be around 1. So omega total, Albert is looking at me like strange. So okay, so omega total is 1. Why? Because omega total should be equal to omega of baryons plus omega of cold dark matter plus omega dark energy. Okay, there are some other ones, but they're really small, like radiation and so on. But let's put it here, omega rad. So this is equal 1. So and this is 1, right? So if I pick this, if I know this value, which is 0.7, and this thing is 0.0, I don't know if I recorded 0.02, I think, 0.05. That's 5%, right?
Yes.
Okay, 0.5. And this is nothing, basically. And then omega dark matter is 0.1, 0.25, let's say. Okay, if I increase omega dark matter to be larger than 0.25, which means picking a sigma v smaller, sigma v, right? Because it means a larger abundance. Then I making the omega total larger than 1. So if it's larger than 1, this has to do with a universe which is with a closed universe. So you overclose the universe. So it was open, but it's not a flat space anymore. It's a closed universe, and that's why you overclose the universe. Okay. Okay, but then this abundance is not consistent with the data. And I say, hey, for now, okay, fine, you picked the sigma v, which is okay with my limits, but you exclude it because you cannot explain the relic density right. Well, not necessarily, because if, okay, it throws out if sigma v 10 to minus 27, but if around that time, around here, something new happened, something new. What is something new? Well, if there's a particle that dominated the energy budget of the universe and decayed, was very heavy, and decayed into light particles. Those light particles, because they are light compared to the heavy particle, they are relativistic. If they are relativistic, then they contribute to the entropy. Therefore, the yield decreases. Then instead of being red, the real curve will be go back to this value here. So it's a way of bypassing, really circumventing the standard vanilla way of computing the relic density. And you can do the opposite. So let's say now I had a sigma v, which was 10 to minus 25, very large. And then my sigma v, let me copy and paste this thing. Come on, Bob. Go. Ah, it's too slow. What? Let's see if I can paste it. No, I can't. For some reason, it's not working. Fine. All right. So I have that curve and over S, and then that's what I expect. But what I saw, and then eventually my sigma v, instead of being this one, centimeter cube per second, was this one. So it means a sigma v of 3 × 10⁻25. So an order of magnitude larger. Well, in this scenario where the sigma v is 1 order of magnitude larger, and then omega h will be, well, roughly 0.01. So 1 order of magnitude smaller. And that's not consistent with the data, then you have an open universe instead of a closed universe, and you don't have a flat universe, you just have an open universe, and which is not consistent with the data, because omega h squared should be 0.1. So how are you going to overcome that? And then I do the opposite. Now assume that some particle that was decayed around this time here, and that particle, instead of decaying to some amount of particles, decayed into dark matter. And then that particle existed and no longer exists and decayed into dark matter. Then the amount of dark matter I have today is the one that I had from freeze out plus the one that came from the decay of the other particle. And then is a way of then going from here back there and getting the correct product density. So I can do both ways. So I can decrease it or I can increase it. But that's everything has to do with particle physics, right? So I'm just assuming a new particle and I'm saying that it decays in a certain way. So this is a way of changing the overall dark matter abundance using particle physics. Okay? And there's another way of changing dark matter abundance using cosmology instead. So let's use the same diagram. So this is this one using, oh, no, come on. Using particle physics. And now let's do, okay, it came back. Come on. Now I'm gonna just delete the whole thing. Using cosmology. So in this case, that's the one that we liked a lot. We worked in the past years. So it goes the following. So I have the yield is N over S. And thus say this is, remember, this, oh, come on. Why can't, what? Why it's not let me, it's a bug. I can't, I'm not, maybe it's my table?
Yes.
Yeah, it's my table. I mean, yeah, it's my table. Man.
The problem is only
And look at this scenario. So let's say in the standard freeze out scenario, that's what I get, where the freeze out happens, and this is x is equal m over t, the same way it was up there. X is m over t. And okay. Now let's think of a scenario. Remember, this freeze out happens when h is equal gamma. H is equal, sorry, gamma is equal h, and h being the Hubble rate and gamma the interaction rate. So if gamma was too large, that's what we consider. We change gamma, so we change the annihilation rate. So if the annihilation was too small, was up here, I had to include something that diluted the dark matter abundance. If gamma was too large, and then I had something to compensate and produce more dark matter. So changing the left side of the equation. Now if I change the right side of the equation, if h was too small, h was too small. So if h was too small, the gamma equaled h before. So around here. And then the abundance is this one. So is when h is smaller than h standard. Let's say lambda CDM.
This H is all added back, right?
Mm-hmm. And now I'm gonna consider this is the standard case. And now I can consider an h which is larger, and then it will take longer to find it. So let's say this one. Then it's a h which is larger than h lambda CDM. So it's the same scenario. I'm just reversing the side of the equation. I'm just changing the side of the equation which I'm changing. But at the end, you see that even though I have a, in this case is this, I have a particle physics model. I like it. For some reason, it's my favorite model. I love it. It's the best one in the world. And people say, hey, Fernando, but your model is excluded. I don't care if you like it or not, but it's excluded. And they say, I will not give up my model. I will not give up on my model. So I'm going to change cosmology to make sure that my model is still consistent. And then you can change your cosmology to make your model consistent. And it's true, you can change cosmology. But the interesting aspect is, you're an experimentalist. The only thing you do in this case is to say whether or not my model is excluded, right? According to data. But I can make my model consistent with your data, changing my assumptions. So whenever you say a model is excluded, it's excluded under certain assumptions, either in the particle physics side or in the cosmology side. So if I change one of those two premises, then your conclusion will also change. Maybe still excluded or maybe not. Okay? So I'm just emphasizing that. Why I'm emphasizing this? Because today we are in an era where the WIMP paradigm, or the standard vanilla dark matter model, is called WIMP, W-I-M-P. Remember WIMP? WIMP model. So WIMP model, weakly interacting massive particles. So in the WIMP model, you expect sigma v to be around 3 × 10⁻26. There's a historical reason. Okay? And then if comes some results from the guys there at São Carlos and say, hey, we use CTA and we excluded sigma v of sigma v, not the thermal, the sigma v of 3 × 10⁻26. So far now the WIMP model is excluded. And no. The WIMP model, if it's not on the resonance, if there are no threshold effects, if there are no blah, 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 many things, then you exclude it. And still, if the standard cosmology is the correct, is the lambda CDM model. Because if it's not, again, you did not exclude my model. You excluded that sigma v, period. You did not exclude my model. Because that depends on cosmology. And you think, oh, Fernando, but this is weird. Why are you going to change lambda CDM? The point is, you should know their data coming from cosmology only. They don't care about particle physics. They're just saying, we're just doing cosmological observations. And those cosmological observations do not agree with lambda CDM. So they have motivations by themselves to go beyond lambda CDM. Regardless of dark matter, regardless of particle physics, regardless. So they do have motivations to do it. And there are multitude of papers where they test whether the lambda CDM is the correct model in certain astrophysical objects, in galaxy clusters, in surfaces, and so on. So they are always testing whether lambda CDM is the correct model. I think today it's kind of known that lambda CDM is not the concrete default model. There are tensions which are statistically significant that lambda CDM is not the correct model. So remember, they do this, they don't care about what we are doing. They just say, hey, we concluded this on our own. And then say, okay, if these guys are concluded that lambda CDM is not the correct model, so how can I say that lambda CDM is the correct model and test the predictions for my model using lambda CDM? Well, if these guys were the experts in cosmology, they're saying that lambda CDM is not perhaps the correct model, who am I to say otherwise? So then perhaps, and then what our job is to see, okay, if lambda CDM is not the model, what's the impact in the particle physics world? And that's what you're trying to do. Okay. That's why I think it's still valid to do this. So you're not gonna, what you're doing at the end is like to showing this experimental community that the limits they provided are important, very important, makes the progress, tell us in which direction we should go, but does not does not mean that their limit should be taken at face value, and that limits sigma v or the scattering cross section of a given mass is excluded. There is no all WIMP models are excluded. No, there are model dependence that goes into that. Okay. And just to finish, I want to cover something regarding indirect detection. Let's think, remember, I'm just thinking of the simplest scenario, not even going to details of more complex models, complicated models. No, I'm just thinking of this. My conclusions rely on the simplest scenario for dark matter. Obviously, if I go to more complicated models, then I can really bypass many of those constraints. So then I have this. So in the early universe, you had dark matter annihilating to fermi-antifermi pairs, which is related to the abundance. And today, what I'm looking at different dense regions of the sky and try to search for gamma rays or cosmic rays that result from those annihilations. Okay, that's what I'm trying to. That's what many of us are trying to do. Okay. And then look at this. And in general, sometimes, let's say many times, this coupling here is equal to this coupling. Now you're going to understand what I'm trying to. So it's G. What's the standard model Z boson, right? So the Z boson couples to fermions proportionally to the same gauge coupling. This has to do with the gauge symmetry at which the Z arises from. But when I go beyond the standard model, this does not hold. I can have models where the mediator couples to fermions, standard model fermions in one way, and to dark sectors, dark particles in another way, with different coupling strength. So this would be a G, and this one would be a G chi, let's say. I won't put G prime because we have already G prime standard model. So G chi, so G for the dark sector. Now think of this following scenario. If M chi, this one is also, man, my table is has a lifetime already, huh? Does anyone know how to solve it? Yeah, maybe I'll do that. Hold on. Where's my pencil? Maybe? No. Could be my pencil too. Okay, it worked. So maybe it was just a bug. So if M chi is larger than MZ, if larger than MZ, then you have this diagram above, and you also have this diagram. Wait, come on. No, this must be a bug because it was working before, right? No. Look.
Puxa o lado pro lado contrário. Puxa assim, ó, o traço.
Traço? Como assim?
Você tá fazendo assim e assim. Faz assim.
Ó, assim não vai não.
É o que eu tô dizendo. Só assim. Vai ter que escrever assim que vai ficar.
Não. No, that's impossible. It must be. É aqui. Hold on, guys. Você sabe trocar isso aqui? Você trocar não?
Cadê a caixinha, professor?
O meu vem aqui, ó.
Porque geralmente ela tem que ter um pegadorzinho para puxar.
Eita, aí não tem não.
Tem que ter um pegadorzinho de ferro. Não sou mesmo, não?
Tem. Yeah, let's see if I can still finish this. No, man. No, see? Even if I... Oh,
Tenta outro programa, professor. Ou Journal, se tiver no computador.
oh, show?
Journal. Journal plus.
I don't have it here. No.
Abre o Jamboard, então, no Google.
This one?
Não. Abre o Google. Não sei se o Jamboard ainda existe.
The what?
Jamboard. J-A-M Board. Yeah.
Vamos ver. Ok.
É o programa, né?
É o programa. Pronto. Okay, so we have chi bar. And then I have this case. Chi bar. Z, fermion, anti-fermion. And I said this is a G coupling and this is G chi. Okay? And now wait, I want to scroll down. Yeah, it's not going.
Talvez seja só isso mesmo. Realmente não tem barrinha ali, a luzinha pequena.
Okay, then I can still write here. Chi bar. I can still have this diagram. Chi bar, Z, Z. So this process here will happen if M chi is larger than MZ, right? And this process will happen as long as M chi is larger than MF. So it means this. Look, if the couplings are the same, this is G chi and G. This process in many Perm space, you can just draw the sigma v of those two cases. You're gonna realize that the first diagram dominates. However, when M chi is larger than MZ, then you have to study. So let's say that M chi is larger than G. G chi is larger than G. If G chi is larger than G, then this second process will dominate over the other one. And then in this case, you have chi bar producing ZZ. ZZ eventually decays into fermion anti-fermion pairs, right? So you get 4 fermions instead of 2. But there is a dilution. So for instance, I had each fermion here would have the mass, look at the difference. Each fermion would have the energy of the dark matter particle, right? In the first diagram, I say, if I'm outside the resonance, each fermion will have an energy equal to the dark matter mass. They'll have a loss of energy because let's say 1 TeV dark matter particle will have a 1 TeV fermion. And now in the bottom diagram, I have 1 TeV dark matter particle producing 2 Z's. Okay? And then the Z decays. When I produce the Z, then the Z decays. So when the energy of those fermions in the final state will be different from the dark matter mass. So the energy of the photons in the final state in the bottom diagram will have less energy. If they have less energy, they produce less gamma rays, they produce less cosmic rays, they produce less neutrinos, less whatever. They produce less neutrinos, less cosmic rays, less gamma rays. The flux of gamma rays, neutrinos, cosmic rays will be smaller from dark matter annihilation. If the flux from dark matter annihilation is smaller, the constraint I get is weaker. So in this case, I'm just tuning particle physics, the mass or the coupling, to make the constraints for indirect detection to be smaller than they are in the standard case. Okay? So then when I see that limit, so let me take a new one. Let me see. Can I clear frame? So when I have this limit sigma v over mass, let me change this.
But it happens because there is an assumption that they do in order to take this value, right?
So the limit from on sigma v are like this, similar to those from direct detection, but not the same. And this limit, okay, in my model, I could have the sigma, let's say my model was here. I say my model was living around there, would be excluded. And then what I do, I increase the dark matter mass. Let's say now I'm around here, I'm increasing the dark matter mass, and I'm still excluded. But then I switch the diagram which is relevant for indirect detection, and then my cross section will be when I'm increasing dark matter mass, I start moving from up there to down here, because there's another diagram relevant. And then some region of parameter space will still be okay with the experimental limit. Because when I increase the dark matter mass, let's think of the following. Flux of gamma rays proportional to sigma v over m chi squared, right? And there is some dNdE there involved. I'm forgetting everything else, okay? I'm just focusing on this. So from this thing only, you can see that experimental limit, the blue curve, weakens as I increase the dark matter mass. That's what the blue curve is showing, telling you. As I increase the dark matter mass, the limit weakens. But in my model, the flux from dark matter is getting smaller when I increase dark matter mass. So at the same pace at which the experimental limit is decreasing, weakening, my model is also producing less gamma rays. And remember, everything what I do in the end is I have a sigma experimental limit is sigma from background plus phi from dark matter. Phi from experimental limit, from the experimental data, phi from background, and phi from dark matter. This thing I have to obey no matter what. But the less gamma rays I produced, the weaker the constraint, right? And the only thing I did was going from this channel to the other one. And now I have fermions. So as I increase the dark matter mass, I opened up a new annihilation channel, and that annihilation channel produces less gamma rays. So if my phi dm decreases, then the constraint I get is smaller. Okay? So a way of bypassing the experimental limits from indirect detection is just, in some cases, is having a new annihilation channel being opened up, and then you weaken the limit. And remember, I'm just taking one case where I have one chi, one mediator. The mediator is just the z coupled this way. I'm not taking any complicated models, considering any complicated models. So, and just to finalize, I have the collider. Which is, you have fermions, quarks, antiquarks, they annihilate. Let's say they produce a Z boson. And then this Z boson, in my case, I was assuming to be coupling to dark matter. But this dark matter particle at colliders is simply missing energy. And detectors such as LHC cannot probe particles which are just simple, just missing energy. They'll just pass through an event and they won't record it because they just pass through. They need something, they call it, to trigger the event. What is trigger? Something has to come out of this. Let's say a gluon, which becomes a jet, or a photon, there. So, and then they say, we have center mass energy of 13 TeV they produced. Let's say they saw nothing plus a photon. So, okay, something happened. I saw a photon, but I didn't see anything else. So this anything else is some invisible, some missing energy, which is the energy missing from the initial state. The initial state was 13 TeV. I just saw a photon with, let's say, 1 TeV, then there is 12 left. So where did the 12 left? Where did the 12 go? And that's okay, what should be the dark matter mass to account for this 12 TeV missing from the 13 that I had in the initial state? Okay, so this missing energy or missing transverse momentum from dark matter has everything to do with observing nothing. Well, I didn't observe anything, but seeing something that I measured. So you always rely on having a trigger or observing something that you can detect. And then you detect the blue one, and then you know that something passed through and you didn't see it. Whether it was neutrinos do the same thing, or dark matter. Okay? But then again, as you see, it's the same case as before. This coupling I call the G. This one could be G or G chi, remember? So the production cross-section of dark matter at LHC is also again controlled by the same couplings. That's why there is a dark matter complementarity, because if you fix G and G chi, I can tell you the signal that you're going to see at colliders, I can tell you the signal that you're going to see in gamma rays, and I can tell you the signal that you're going to see at detection experiments. Yeah, but it's connected. But let's say we are talking about the detection. So three completely different detection techniques, they are governed by the same couplings. So then that's the interesting aspect of this, which that's the thing I like, because if you see something collider, they measure the cross section. Say, look, I saw something, I saw a signal. And then what we're gonna do? What's the G couplings that we need to have to get the cross section these guys measured? This value. And say, hey, direct detection experiments, guys, run your detector because you're gonna see a signal with this cross section. And they're gonna run it. If you don't see it, there's one conclusion only, because what you saw at colliders was not dark matter. Because if it were, you would have seen a signal in direct detection experiments. The same for indirect detection. Hey guys, you can beat up a telescope, search, push down the threshold, the sensitivity to annihilation cross-section, because you're going to see annihilation, a signal from gamma rays, which is consistent with some sigma V of this value. Because I saw something at a collider, and I saw something at direct detection experiments, and you must see something. Because if I saw in two, no way, there must be dark matter. Colliders, I want to emphasize, colliders do not see dark matter. Colliders see missing energy. Missing energy could be a neutrino. Missing energy could be a particle that is long-lived, just pass through and decay outside of the detector. LHC, if you have a detector at the side of this room, a particle comes through, I detect, I saw a particle. Let's say the particle is missing energy, okay? So I don't see it, right? But I saw something happening because I saw a photon, I saw a gluon. And then from missing energy reconstruction, I say, look, something passed through because I saw a photon with 1 TeV. I had 13 TeV in the beginning. Something must have just passed us, and we haven't seen it. Okay, fine. I concluded something passed, but I don't know what was that something. Passed. I say, look, something passed, fine. But I don't know if that something decayed just outside this wall. I don't know that. My detector is the size of this room. How can I know if there's something decayed just outside of the detector? I can't know that. I can't know if it decayed 1 kilometer later, 100 meters later. I have no idea. So I cannot claim that I saw dark matter at LHC. because I cannot distinguish neutrinos or long-lived particles from dark matter. I can't. Okay? Make sense? But in which sense colliders can say something? We have a direct detection experiments, observe something consistent with some mass, coupling, whatever. And then Leticia has a telescope and detects a signal from dark matter which is consistent with the same coupling and mass. And I say, hey, LAC, search for this coupling and mass because you're going to see something pass through. And, well, you're going to measure some missing energy event. And that's something that's missing, is not anything, is dark matter. You see? I cannot claim it before, but I could, let's say, attest what they observed later and confirm the signal. And many collider friends, they get angry when we say this. Hey, you are not a dark matter discovery machine. No, we are. It's not. No, you're not. No, we are. It's not. You can't discover dark matter. You can confirm whether someone else observed dark matter. And then I used to say this for many, many years. And this is true, but then there's an exception. What is the exception? That's the one example someone gave it to me. For now, you're saying that we are not a detector machine. But let's consider this scenario. I observed, LHC Atlas was a guy from Atlas. We observed a signal which is consistent with missing energy. Okay? You observe. We don't know. It's fine. It's true. We don't know if it's dark matter. Fine. What we detect and we measure, we have an excess of events consistent with missing energy. And we can't claim it is dark matter. Fine. But then we tell, as you said, we tell our colleagues from direct detection to search for the same couplings and mass, and they find something. We ask our friends from indirect detection to search for gamma rays for that signal, for that coupling mass, and they measure the gamma rays. Who do you think is going to get a Nobel Prize for discovery of dark matter? Say, okay, perhaps you're going to be part of the Nobel Prize because they detected first. They couldn't claim it was, but they were part of the discovery.
The same would happen, for example, with direct detection.
Exactly. But they still could get it, you know?
Yes.
So direct detection we will always get, but colliders only if they do it first. Because we can claim the discovery of dark matter without colliders.
Because they give the direction.
Yeah. We can claim the discovery of dark matter without colliders, but if colliders see a signal first, yes, they can be part of the discovery. Okay? Because one thing you should emphasize, the annihilation cross-section of dark matter, remember that depends on the local density of dark matter. And the direct detection also depends on the local density of dark matter. But the one goes with rho squared for the scattering, which is just one rho, which is one particle. One number density for scattering, and number density times number density for annihilation. So they depend on the local density of dark matter. So the signal depends on the density of it's not the density of neutrinos, it's the density of dark matter. So if they do see a signal, it's tied to the number density of dark matter. Colliders produce something which has nothing to do with the density of dark matter. That's why one can claim a discovery, whereas colliders can't. Okay?
So I have wondering now about something like we have a density of dark matter particles in the local
neighborhood.
Yes. So in the solar system, so we are doing collisions of protons and neutrons. I say protons because of let's see. And in the event we see some anomaly, for example, something disappeared and something new just disappeared in the collision. I mean, in the event.
Long-lived.
Yeah, it could be not necessarily produced by the collision of the particles itself, but after the collision, it's like the particles. Let's say there is an event that's very big, and it took, for example, one GV, let's say, and one TV, better, and then we saw that anything it's like something happened and then here it disappeared entirely, but we can't say that it was from something in the event of the LHC itself. It could be something that happened due to the density of the dark matter particles in the local system.
Yeah, I see. So he's contemplating the possibility of observing astrophysical process inside the detector of LHC. The problem is that the probability of that event happening is much, it's so small that it's insignificant for colliders. If you just think of the scattering rate of dark matter experiments, it's just so small, so small. It's like you can't see it. It's too small. Any questions?
Just a question. In fact, a question and a comment. Why do colliders search for the transverse in this momentum? If, for instance, you can search for the longitudinal one, because I know that from some models, the Ensino model, you can produce particles in the longitudinal way.
So the point is, when you have collisions in this plane, like this,
yeah.
Okay, so I will have much better handle on the amount of momentum going in this vertical axis, transverse to the collision.
Okay.
So the sum of momentum here now, for instance, in the vertical plane is 0, right? When the collision happens. So whatever I detect, I know that the sum of the transverse momentum has to go to 0.
Okay, right? So it's about the symmetry of the process.
Because the symmetry of the collision. So the collision does not come here and so on. Wow, it comes right here. Obviously, I could move my frame in order to always have the transverse momentum to be 0. But what happens is the collision happens right here, and the transverse momentum the sum of all transverse momentum have to be 0 for not for dark matter, for everything.
Yes.
And the collision happens here. But remember, I don't know exactly the energy of a quark. And I don't know exactly the energy of a quark here. So maybe there is some mismatch between the energy of this particle and this one. And then you might have some momentum, longitudinal momentum, because a proton does not have an energy of 13 TeV. Yes, a proton does have, but the constituents of the proton don't have a precise energy. There's a parton distribution of momentum in the quarks. So I don't know the individual energy of each quark in the collision, but I do know that the transverse momentum of all particles should be equal to 0, the sum of all of them, right?
Yes.
Whatever the energy they had in the initial state. I know the sum of the transverse momentum has to be 0.
Okay. Yes, understood, I think. Yes, about the comment I was going to do. I think it's interesting because usually when you see interact detection limits, usually the people plot the limits from primary channels, right?
For what?
Primary channels, like BB, W+, WS. But in fact, if you see well, what you have to do is use the branching ratio that you can get from a model. So the limits will be different. And I think it's fun because usually people don't see it, and it's somehow hard to see some papers that make that. I think
it's
important.
True. And the point I'm trying to make, Luca, is I think I'm done here. The point I'm trying to make is deeper than that. So if I have dark matter producing pairs of vector bosons or scalars or whatever, if those scalars are produced on shell or off shell, makes a difference in the DNDE you compute.
Yes. Okay.
So even if the branch ratio is the same, even if the branch ratio is still the same. So let's say that 100% of my dark matter goes into ZZ goes to E plus E minus Z plus E minus. So it's 100% is 1%, right? So it's branch ratio is equal 1. But the DNDE you compute, whether that ZZ was on shell, off shell, differs.
Okay.
So if that particle was produced on shell or off shell, it will be different.
Okay.
So there is a mass relation between, for instance, dark matter particles matches the mass of the final state of the Z boson. You have a yield which is sharper than the one if the mass of dark matter particle is much heavier than the final state, the Z final state. So you have got a softer spectrum for the gamma ray yield. So even if the range ratio continues to be 1.
Of course.
So the particle physics only, even if the range ratio is equal 1, it still will alter the DNDE you get.
Okay.
So if you just put a reference DNDE as a function of the dark matter mass and the Z mass, you're gonna see it is different.
But for instance, Chirelli spectra accounts for it, or it doesn't? From
What?
PPPC, the spectra from Chirelli, PPPC.
Yeah, from Chirelli, it doesn't, because Chirelli assumes that the final state is much lighter than the dark matter mass.
Yes, yes.
They assume that the particles in the final state, their mass is negligible.
In fact, yes. The spectrum is low.
It's soft.
Low, yes.
So that's what they assume. So you needed to run Pythia, I assume, in order to get the correct spectrum.
Yeah.
Okay.
Okay. Thank you.
Any further questions? Because I think I'm done. No? Just me and Luca. And I know that are attending classes, so it's good that it's being recorded. So
yeah.
All right, so I think I'm gonna finish. It was nice seeing you all for this 10 lectures, during these 10 lectures. So it was quite exhausting. All right, and Luca, send me a WhatsApp message, then we talk, okay?
Of course.
All right, bye.
See you. Bye.